Thanks for watching my talk about graph isomorphism and quasi-polynomial time parameterized by treewidth. The graph isomorphism problem is a classical problem with unknown complexity status. The problem asks whether two given graphs G and H are isomorphic. That means there's a bijection between the vertices of the graph that map edges to edges and non-edges to non-edges. The graphs you can see here, they are indeed isomorphic, as you can see. So there is a bijection mapping edges to edges and non-edges to non-edges. What do we know about the problem? One of the first results was given by Filotti, Mayer and Miller in 1980. They showed that for graphs of bounded Euler genus, the problem can be solved in polynomial time, where the degree of the polynomial depends linearly on the genus of the graphs. 2 years later, Lux developed a group theoretic framework in order to tackle the problem. With his pioneering work, he could show that for graphs of maximum degree d, the problem can also be solved in polynomial time. And again, the degree of the polynomial depends linearly on the maximum degree of the graphs. 1 year later, Babay and Lux could extend this result to the graph isomorphism problem in general. With some degree reduction trick given by Lachenko, they could prove a time bound that Babay calls moderately exponential time. That's still an exponential time bound, but the exponent grows much slower than the linear function. Their algorithm runs in n to the square root of n if you don't care about logarithmic factors in the exponent. For graphs of treewidth t, Bodlander could prove an polynomial time algorithm where also the degree of the polynomial depends linearly on the treewidth. It's a relatively simple algorithm that uses a dynamic programming approach. 1 year later, Ponomarenko could prove a unifying algorithm for graphs of Hartwigger number h running in n to the poly h. After more than 2 decades, Babay had this breakthrough result where he showed that the graph isomorphism problem for graphs in general can actually be decided in quasi-polynomial time. That's an exponential function, but the exponent of this function is some polylogarithmic function. The c you can see here can be chosen as 2 according to Harscott analysis. Babay's breakthrough result leads to a lot of questions. One natural question is, for which parameters k can we solve the graph isomorphism problem in n to the polylog k? Such a running time bound would clearly generalize Babay's quasi-polynomial time bound, as the usual parameters as treewidth of the graph or the genus of the graph, or maybe the maximum degree of the graph, are usually bounded by n, the number of vertices. On the other hand, such a running time would also generalize the results that were proven in the 1980s. The first result given in partial answer to this question was proven by Groenneun and Schweitzer in 2018. They proved that for graphs of maximum degree d, the graph isomorphism problem can actually be solved in n to the polylog d. Another result proven by my colleague Daniel Neun, which will also be presented at ICALP 2020, is that also for graphs of bounded Euler genus, we have such a running time n to the polylog g, where g is the Euler genus of the graphs. My main result which I want to present is that for graphs of treewidth t, the graph isomorphism can be solved in n to the polylog t, generalizing Babay's result in the n to the t algorithm given by Bodlander. After I talked a lot about graph parameters, I think it's important to explain them and explain how these graph parameters relate to each other. The genus of a graph describes the minimal Euler characteristic of a surface in which you can embed the graph. The maximum degree clearly describes the maximum number of neighbors of a given vertex in a graph, and the treewidth of the graph somehow describes how tree-like the graph looks like. For the graph class of bounded Euler genus and the class of graphs with maximum degree d, we already have a quasi-polynomial time algorithm. For graphs of genus G, this algorithm will be presented at this ICALP by my colleague Daniel Neun, And for maximum degree D, there's an algorithm given by Grohe, Neun, and Schweitzer. I want to talk about treewidth in this talk. Okay, let's give some examples. For example, there are graphs of unbounded treewidth with bounded Euler genus and bounded maximum degree D. A classical example for this is a grid graph. This is a planar graph, so the Euler genus is 0, and the maximum degree of the grid is bounded by 4. But however, if I make this grid larger and larger, it can be shown that the treewidth grows with the size of the grid. Actually, the treewidth of an n times n grid is something like n. However, it's still a planar graph, and the maximum degree of this graph does not grow when the grid gets larger and larger. Let's look at some other examples. For example, what are graphs of bounded Euler genus and bounded treewidth that have unbounded maximum degree D? A classical example for this is the so-called star. This is a tree, so the treewidth of this graph is 1. It's a planar graph, so it has genus 0, but the maximum degree gets larger and larger if you increase the star. Then finally, a prime example for graphs of bounded treewidth and graphs of bounded maximum degree are these ring graphs. Basically, you have a cycle and you connect the vertices only in the local neighborhood of the cycle. So let's say you connect two vertices if their distance in the cycle is at most c for some constant. Then if you make the cycle larger and larger, the degree of this graph will not grow. And also it can be shown that the treewidth of this graph will not increase. The treewidth of a ring is somehow the thickness of this ring, which will not grow if the ring gets larger and larger. However, it can be shown that the genus of a ring grows linearly with the size of the cycle. So at the first glance, these graph parameters seem fairly unrelated. But actually they are not that unrelated. In fact, if you have a graph of bounded treewidth T, there's a tree decomposition of the graph, so such a decomposition here into bags, such that the adhesion width, that is the maximal intersection of two such bags, is bounded by the treewidth, and you can assign to each bag a structure of bounded degree. So roughly speaking, you can decompose a graph of treewidth T into bounded degree parts. It does not mean that these graphs induced on the bags are actually graphs of bounded degree, but I will not define what this structure of bounded degree means. It's actually some group theoretic characterization that restricts the composition factors of the automorphism groups of these graphs. However, the important thing is that we can use this bounded degree structure to apply the bounded degree isomorphism algorithm that was developed by Grohe, Neun, and Schweitzer. I'm not quite sure which authors I should reference for this theorem, since the theorem has a long history. It's based on the clique separator decomposition that was first introduced by Leimer and then Lokstanov and some other authors. They were the first authors who actually used this clique decomposition in an isomorphism test where they gave an FPT algorithm for the problem. And they used this technique of k-improving a graph, which goes back to Bootlander. And then maybe we were the first authors who actually observed this bounded degree structure on these bags and characterized the orthomorphism groups of these graphs. Furthermore, we have additional classical properties. We can actually compute this decomposition in polynomial time. And the second important property is that this decomposition is isomorphism invariant. This somehow means that the decomposition is compatible with isomorphisms. I can try to explain this in a picture. So, what does isomorphism invariance mean? Assume you have given a graph G and you have given some isomorphic graph H. So there's a bijection between the vertices preserving the structure of these graphs. Then assume you make this decomposition on the first graph G and you make this decomposition on the second graph G. Then isomorphism invariance means that each isomorphism between the graphs also maps the decomposition of the first graph to the decomposition of the second graph. So all isomorphisms preserve the decomposition. In other words, each isomorphism maps a bag to a bag in the second graph, and it cannot map a bag somewhere in between. And this property is important for isomorphism testing, since we want to decompose the graph in structurally equivalent ways. And we do not wish to compare decompositions that have nothing to do with each other. So with such a decomposition, I can sketch the algorithm for graphs of bounded treewidth. Basically, we apply this decomposition to G and to the graph H, such that each bag has this structure with bounded degree. Then on the bags of bounded degree, we can use this isomorphism algorithm for bounded degree graphs, which is given by Grohe, Neun, and Schweitzer. And this algorithm runs in the desired time bound if the degree is bounded by some polynomial in the treewidth. To obtain the set of isomorphisms between the entire graphs G and H, we somehow need to merge these isomorphisms in some meaningful way. And this will be explained on the next slide. This motivates the multiple Coset isomorphism problem. In this setting, we have a decomposition of the graphs and these bubbles or pickles, or call them whatever you like. And we are interested in the isomorphisms between the entire graphs. What we have given is this set lambda ij. These are the isomorphisms between basically the subgraphs. So lambda ij is the set of all isomorphisms between G induced on AI and H induced on Bj. These sets can basically be computed with the bounded degree isomorphism algorithm if these subgraphs have the bounded degree structure. If, for example, I would intersect lambda 1, 1 with lambda 2, 2 and lambda 3, 3, of course induced on this set V, otherwise I can't intersect these bijections, I would obtain all isomorphisms from G to H that map AI to BI. So in this picture, A1 to B1, A2 to B2, and A3 to B3. But of course, this is not what we want, because there could also be an isomorphism mapping A1 to B3 and A3 to B1. So what we actually need to compute is described in the following problem. We have given two sets V and W, and we have given cosets lambda ij restricted to V. These are sets of bijections between V and W. And what we want to compute are all bijections between V and W that can be extended to an isomorphism between the entire graphs. That means there's a permutation, so basically a matching between the components in G and the components in H, such that phi is contained in lambda I pi I, and this holds for all I. This is the multiple Coset isomorphism, and the main work in my paper is to solve this problem. We could show that the problem can be solved in n to the polylog size of V. So if you recall the decomposition, you remember that the intersection between the bags is bounded by some polynomial function in the treewidth. So this means that the exponent will be some polylogarithmic function in the treewidth. The proof of this is very complicated. It's about 30 pages long, but I want to sketch it a bit, but I wouldn't even call this a proof sketch. I just want to explain the techniques that I used in order to solve the problem. It's actually a purely group theoretic algorithm based on Babai's algorithm. And it builds on Babai's method of local certificates. Roughly speaking, the idea is to consider so-called test sets. And these are sets of logarithmic size So the number of test sets is clearly bounded by a quasi-polynomial. So you can iterate through all these test sets. So assume you have a pair of test sets T and S in the graph. And the algorithm basically distinguishes between three cases. In the first case, the test set distinguishes the components. So for example, in the graph, it could mean that the first test set has two neighbors in the component A1, three neighbors in the component A2, and only one neighbor in the component A3. Actually, that's not exactly what happens there, because as I told, it's a group theoretic algorithm, and actually these test sets aren't even subsets of the vertices. Instead, they are subsets of some permutation domain on which you find a group, and you also don't consider neighborhoods here, but that's maybe just a very rough idea. But however, if you have such a setting that by fixing a test set you can distinguish components, then the same must happen in the second graph. Otherwise, the graphs are not isomorphic. But then you know after fixing these test sets, so if you just consider isomorphisms mapping T to S, then these isomorphisms must also map A3 to B2, since the number of neighbors must match. And then basically the problem reduces to a group intersection problem. So actually by group theoretic methods, this intersection problem can be solved in quasi-polynomial time by using also Babai's algorithm. Then we could be in a second case where these test sets give you a partition of the components. For example, T have three neighbors in A1, but only one neighbor in A2 and A3. This defines you a partition after fixing this test set. And in this partition, A2 and A3 would be in the same part. And then you can use this partition to recurse on that. The final case that is left is that these components look fairly identical. This means even if you fix such a test set, you cannot distinguish between these components. And there might be still an automorphism swapping these components. And actually, it can be shown that in this case, one can use these symmetries to actually find orthomorphisms. And these orthomorphisms then can be exploited by an isomorphism algorithm in order to reduce some search space of the algorithm. So let me conclude. I gave an algorithm for graphs of treewidth T running in n to the polylog T. Basically, we decompose the graph into bounded degree parts. Then we use the bounded degree isomorphism algorithm by Grohe, Neul, and Schweitzer to compute the isomorphisms between these parts. And then we merge these parts, which was the main work and which was done by group theoretic methods building on Babai's algorithm. I want to mention some open problems. One question is, can we extend this result to graphs of bounded Hartwigger number? The Hartwigger number of a graph is the size of the largest clique minor that occurs in the graph, and this class of graphs generalizes graphs of bounded genus and bounded treewidth, as they cannot have large cliques as a minor. Actually, me and my co-authors could solve this problem, generalizing the bounded genus and the treewidth algorithm. This paper isn't published now, but a preprint can be found on ICALP. We also think that our decomposition techniques, which also implies restrictions on the orthomorphism groups of these graphs, can help to prove a conjecture stated by Babai. He conjectured that there's a function f such that for all graphs of Hartwigger number h, the composition factors of the orthomorphism group are either alternating, that means isomorphic to the alternating group, abelian, or smaller than f of h. Even if it's not an immediate consequence, we think that our techniques might be helpful here. Can we ask whether we can extend our techniques even to graphs excluding the topological subgraphs? These would also include the graphs of maximum degree B. The last question I want to mention deals with fixed parameter tractability of the graph isomorphism problem. One should mention here that for graphs of treewidth T, or there is actually an FPT algorithm. And similarly, also for graphs of genus G, the graph isomorphism problem can be solved in FPT time. The only part that's missing here in the picture are the graphs of bounded degree. So it's a natural question whether the graph isomorphism problem, parameterized by maximum degree D, can be solved in FPT time. If this is actually the case, then one could also hope for FPT algorithms for graphs of bounded Hardwiger number, or even graphs excluding a topological subgraph. Thanks for watching my video.